Okay, hi year 13. So just before we get started today, if we just do our wee retrieval roulette. So pause and answer these for me, please. And here's your answers. So that question 2 was how to find the total resistance of two resistors in parallel. So either 1 over RT equals 1 over R1 plus 1 over R2, or RT equals R1 multiplied by R2 over R1 plus R2. The rest of them I think are okay to mark just from that. So again, pause, get those marked, and then we'll move on. So open up your notes at page 129 for me, please. We're going to start our motion topic today, and today's going to be a wee quick one, okay? So first of all, we're just going to get to grips and remind ourselves the difference between distance and displacement and speed and velocity, and then we're going to have a look and remind ourselves the rules, because there's nothing new here from GCSE, but we're going to remind ourselves the rules of distance time graph, displacement time graph, speed time graph, velocity time graph. Okay, so just to remind you, distance and displacement, the difference between those, distance is scalar and displacement is a vector. So that means with displacement, direction matters. So the best way actually to describe it is with this wee picture down here. Let me see. So displacement is a scalar quantity, doesn't depend on direction. Displacement is a vector quantity, it does depend on direction. And then the definition, if you write that in for me. So the definition of displacement is the distance moved in a particular direction. So little diagrams like this are always used to explain the difference between distance and displacement. So say you travelled from Cookstown to Belfast, your total distance travelled would be all of this distance all added up together. But your displacement of where you are from where you started is just this distance here, and you would always state it with a direction. Okay, so that's just what that is saying in there. So when you have arrived, you've actually travelled 80 kilometres, but your displacement is 50 kilometres east of your starting point. So you've ended up 50 kilometres away from where you started, but you've travelled 80 kilometres in the meantime. So that is the difference between distance and displacement, and we need to be careful in questions whenever we are reading about those. Now, you know the equation speed equals distance over time. It's one of those equations everyone knows. I reckon it's probably my least favourite equation because it gets misused so often. Speed equals distance over time only works if you have something travelling at a constant speed, or if you want to work out the average speed something's travelling, so you would use the total distance divided by the total time. Honestly, I try to avoid using speed equals distance over time as much as possible because of this, because people use it incorrectly. It's so easy to do. People will use it if something's accelerating, they will try and use speed equals distance over time, and it's just a wee silly mistake. And one of the most common ones actually at AS is whenever we're reading information from graphs and people using speed equals distance over time when they shouldn't. Anyway, that's my slight rant over. Let's work our way through this page here. So definition of speed. Speed is defined as the distance moved per second. Speed is a scalar quantity. It has magnitude and a unit, but not direction. So average speed, total distance travelled divided by total time taken, which you can just write S equals D over T. Please remember that this is just for either constant speeds or average speed. Then velocity, it's a vector, so it's the vector version of speed. I always think of it as. It has magnitude, a unit and direction. It's defined as displacement per second. So the average velocity for a journey is the final displacement divided by the time taken. And the way we would write that would be V equals S over T. So annoyingly, we use S for speed and we use S for displacement. Does my head in. What was I going to say there? Oh, see this? See the average velocity equals final displacement divided by time. That is why if something goes in a complete circle, then its final displacement is 0 and it's ended back where it started. So something like that that's travelled in a complete circle, its average velocity will be 0 because its final displacement is 0. So 0 divided by however long it took is still going to be 0. Okay, and then units for both speed and velocity are meters per second. Okay, acceleration. Sorry, slipped into GCSE mode, ms to the -1. Okay, so acceleration, the definition of it is the rate of change of velocity with time. So it's just a measure of like how fast something is speeding up or how fast something is slowing down. Because it's the rate of change of velocity with time, there's another wee funny thing with that. So because velocity is a vector and velocity will change even if something's traveling at a constant speed, the velocity can change if the direction is changing. So something can be accelerating if it's traveling at a constant speed, but if its direction is changing. So like satellites in orbit around the Earth, they would be accelerating even though they're going at a constant speed, just because their direction is constantly changing. This is going to come up in some of the wee questions later on. It's just saying things as they're popping into my head, sorry. Okay, so acceleration is the rate of change of velocity with time, and it is a vector quantity. Units meters per second squared, because if you're dividing a speed or a velocity, which is meters per second, by time, seconds, meters per second, it simplifies to that. Now, just be careful, if something's speeding up, then it'll have a positive acceleration. If it's slowing down, it'll have a negative acceleration, but that will be stated as a positive deceleration. So just be careful with questions, whether they're asking for acceleration or deceleration, and give the right sign for that. Okay, so an acceleration is described as uniform if it is constant. So if something's accelerating at a constant rate, then that would be a uniform acceleration. And that means equal changes of velocity take place every second. When the acceleration is non-uniform, which we don't deal with in physics here, I don't think we do it A2 either. We are always just uniform acceleration. In maths, you do non-uniform though, I'm pretty sure. So when the acceleration is non-uniform, the velocity changes that take place every second are not equal. So we'll not really have to do any calculations with that. Well, maybe the odd one from a graph, but we'll talk about that. There's our equations. Change in velocity divided by time. More commonly, A equals V minus U over T. You'll all recognise that. Okay, so in our notes, I've only really included displacement time graphs and velocity time graphs. Similar rules apply for distance time and speed time. Oh, did I do speed? No, I didn't. Okay, so similar rules apply for the scalar equivalent of these. So a couple of rules that we need to know, and again, I know I'm going quick, but this is just refreshing this in your memory, I hope. So displacement S against time. Something like this is going to show a constant velocity because the change in displacement per unit time, like every second, the displacement is increasing by the same amount. So that's a constant velocity. It's traveling at a constant speed or velocity. And the rule that we need to remember, the gradient of a displacement time graph will tell us the velocity. Okay. So something like this, because the gradient of this is constantly increasing, do you see how here we've got a really shallow gradient, and then here it's much steeper? Something like this is speeding up. Okay. Now, remember I said people sometimes do accidentally use speed equals distance over time incorrectly from graphs. This would be one of the times that they would do that. So because this here isn't a constant speed, you can't just there's one particular exam question I'm thinking of where it's I think it's a time of 4 seconds, and it asks you to calculate the velocity at that point. The most common mistake that people will make is they will go to 4 seconds. So let's say it's here, right? They'll go up, they'll read off the displacement, and they'll do velocity is displacement divided by time, or speed equals distance over time. But that's wrong, because that would be working out as if this had been traveling in a constant speed, so as if that was a straight line. So that's incorrect. So in that case, what we have to do is we have to draw a tangent to the curve. So say it was this time that we were looking at in the question. You go to that point on the curve and you draw your tangent, which is just a line which just touches the curve, and you're trying to use that line to represent the steepness of the curve at that one particular time. Okay, then you would calculate the gradient of that tangent there. Okay, so let me read through what's here. A displacement time graph that isn't a straight line shows an acceleration. I will draw in other versions of this in a wee second. To get the velocity at a certain time, you need to draw a tangent at that point. Everyone forgets that, right? and calculate the gradient of the tangent. So let's see, can I do this without messing it up? This here shows an acceleration. This here, let me see, I want it to be getting steeper, yep. So if it was like that, that would also show an acceleration, because look, it starts off not very steep, gets steeper. Because remember, the gradient is the velocity. So this here is also an acceleration. One like this would be, if that's displacement time, would be a deceleration, right? Because it starts off steep, gets less steep. And then, let me see, this here, this one, if this was displacement time, that would also be a deceleration as well, because it starts off steeper and gets less steep. Okay, so a couple of wee questions at the bottom of this page. Where did I put my ruler? Draw a displacement time graph showing an object that is stationary. So displacement time, if it's stationary, then that means as time continues, its displacement isn't going to change, it's just staying where it is. So nice wee horizontal line. Oh, an object decelerating. It can be either one of these two. Let's just go with that one. Let's write a wee note there actually. Gradient getting less steep. Okay. And then C, an object that moves with a constant speed in one direction, so displacement time, then moves with a slower constant speed in the opposite direction until it ends up back where it started. So let's go constant speed in one direction. I know they haven't given us details, but okay, we'll just improvise. Constant speed in one direction, and then a slower constant speed means the magnitude of the gradient has to be smaller. So it has to be less steep. Haven't given myself much room there. I might extend that axis. Okay, sorry about that. So constant speed in one direction is this. Slower constant speed in the opposite direction, smaller gradient, until it ends up back where it started. So that's how I knew to go back here. So this is horrendously unrealistic. You'll notice that in a lot of these graphs, we sort of act as if something can go from a constant speed in one direction and then all of a sudden constant speed in the other direction. In reality, there would be wee curves involved in that, but we live in a wee dreamland in physics. Okay, page 132 then, velocity time graphs. A couple of rules that we need to learn about that. First one is that the gradient of a velocity time graph gives us the acceleration, and the area under a velocity time graph gives us the displacement. So something like this, where as time goes on, the velocity is increasing uniformly, would be a constant acceleration. We will get to this in a little bit, but you need to be careful with remembering about the magnitude of the, the magnitude of the velocity, because something like that, so would be a deceleration because the magnitude of the velocity is getting smaller. But we'll see in this wee graph underneath how whenever we go to the opposite side of the x-axis, which we will do with velocity because it's a vector and has direction, so you'll have positive and negative velocities, then it's not like this slope in terms of left to right, up to down that we need to think about. We need to think about the magnitude of the velocity. So yeah, this here, I don't know why loads of people forget this wee fact, but they do. But the area underneath this, so if you had a graph like this and you were asked for the displacement, you would just be calculating the area between this line and the x-axis using the numbers on the scale. So it'd just be the area of this wee triangle. That's it. Okay, so let's look at this one, right? So in this wee section, we've got a uniform acceleration because the velocity is increasing linearly. It's increasing the seat back at a constant rate. Here, it's traveling at a constant velocity. So a horizontal line is a constant velocity. Here, it is decelerating. Now, the rate of deceleration is like much higher than here because it's steeper. then it stopped for a little while. Now, this is what I was rambling about a wee second ago there. See here, I think it's nearly our habit to see that as like a downwards line and think, oh, deceleration, but it's not, because going from here, let me get something to point with, going from here to here, we're getting further away from zero. The magnitude of the velocity, so it's going to be like -1, -2, -3, -4, -5, is getting bigger. So this wee line here is accelerating, it's getting faster, but it's in the opposite direction, which is why it's underneath the x-axis, why it's negative now. Constant speed, and then again decelerating here because it's getting closer to zero. So we are conditioned, I think, to see a line like that going up the way from left to right, to think that means increasing or getting faster, but it's not, because we're getting closer to zero. Now, down here, if this imaginary journey here you were asked to calculate the displacement, well then you would work out the area of this, which you can either do by splitting into like a rectangle and two triangles, or if you remember the rule for calculating the area of a trapezium, it would be this. So remember, A and B are the two parallel sides, so that one and that one, and then H is the perpendicular height, so that distance there. Hardly anyone ever uses that. I don't really know why. People tend to prefer just to split it into rectangles and triangles. It's up to you. So anyway, you would work out this area here, because that would tell you how far this object had gone in the one direction. Then you would work out this area, but because that was in the opposite direction, you would take it away. So that's what I've said here. The displacement is area 1 minus area 2. So for area 1, let's say they started here, they've gone to here. Then for area 2, because it's in the opposite direction, they're going back here. So they've ended up like this far away from where they started. So if we work out this distance, then work out this distance and take it away, then we'll end up with that one. Hopefully that makes sense. Now, be careful, because if the question asked that, that's what you would do. But if the question asked you for the distance, it would just, like the distance travelled, I should have said, it would just be area 1 plus area 2. Okay. Right. I think that's going to be us. I just want you to do the questions on page 133 for me. Then I don't want to do the next one because I want to spend a wee bit more time talking through that graph. You'll be delighted to hear, because it's a good one. It's one of those graphs that people misinterpret all the time. So I do want to spend a wee bit more time on it. So for now, if you just do the questions on page 133, and then that's us. Bye.